your stuff in software without having to know much about real-time programming. So, for example, for the channel reader to tag to reader, you can pre-compilate all your symbols, just store a buffer, and you say, hey, send it to the reader this and this time. So I think it's very convenient how it currently is. And now you also understand why you have all these debug output features on the OpenPCD device, this U.FL outputs, because you have this U.FL outputs on the OpenPICC. You can create your modulation patterns, see it on one channel on the oscilloscope, and you can see how they result in modulation, demodulated patterns on the OpenPCD. So you have the whole chain, and you have full control of every aspect of the protocol, of the analog part, of the digital part, and you can quickly resolve problems. And it proved to be very, very helpful already. This was our first prototype. First time we had fear because the reader field was extremely strong, even if it's not capable of traverse a range of, say, more than 8 centimeters. If you simple task like having an oscilloscope wanting to measure on OpenPICC, it automatically forms some loops. You can't remove them really, and you have the very strong carrier everywhere on your desk. It's in the lamp, it's everywhere. It's everywhere with a strong 13.56 megahertz signal, and you can't see anything. Therefore, for the first prototype, we said we want to play safe. We have one PCB to get a design that is always the same, so we don't have a wire-wound antenna. And we keep it separate from the actual device, from the actual circuit. There is also another topic. There were also two possibilities to solve this topic in software and to solve it in hardware. But as I indicated, we want to make it as simple as possible. So, for example, if you look at modulation, demodulation patterns, they are naturally all aligned on a timeline, and you have a clock or whatever where these are relatively aligned too. But in this particular case, as I indicated, we use the reader field to generate this 13.56 megahertz digital signal, which is derived by our timer signals to our internal clocks. It's used all around the place for our timers, for our counters, and whatever. But the problem is, if you have certain cards, the modulation is 100%. This means automatically that the signal is away, and after a given time, it's there again. But during this time, you naturally don't get any cycles. So it's like the world had stopped for the Open PICC card. For example, the pulse width ratios won't match anymore because each modulation pause will only be 1 or 2 clocks instead of the real amount of clocks, and you had to do dowdy hacks to get meaningful signals out of that. So therefore we decided it's a good idea to use a PLL to lock it to the carrier signal and to use this to maintain the carrier phase correct while the carrier signal is away during a modulation pause. And this proved also to be very helpful because then you can instantly dump the data you got over DMA. You just, for example, assign, for example, an underscore to 0, say a age to high level, and you can instantly print it on a console and you see the bit pattern like you would see on an oscilloscope. This was, by the way, also main design criteria, that the device itself can be set up and operated without special equipment. It is meant to be, if you have an oscilloscope, it's obviously fine, but you don't need one to operate it. And if we have a logic analyzer, it's fine, but you don't need one to operate this. So therefore, we integrated these core features like being able to sample a signal at a high frequency, to be able, for example, to tune the antenna without an oscilloscope. We integrated all these features inside this board, so you, in our opinion, you don't need any special equipment to operate this device. So it's self-contained, basically. Okay, this is how it looks like. It's for the sake of coolness, it's credit card sized. It all again is 4 layers. You see again the 4 turns, and as opposite to OpenPCD, we choose a white as an opposite to the reader. So this is the and you again have a JTAG adapter, but in this case it's really helpful, because to maintain that such tight timing, you definitely want from time to time use assembler to, for example, if you have a high frequency interrupt routine where you want to do some strange stuff, you think you want to do it in assembler. And then a JTAG interface helps greatly. For example, if you're unsure that your code hasn't trashed, for example, internal registers, you can stop it at each time, read out a register, and let it running. So there are possibilities, and if you're interested, we can point you afterwards to places where you can get such JTAG adapters freely. There are open source projects around this, so there is a possibility to get them at reasonable pricing. But you have the same concept, the debug interface. You can do again your printf stuff, and so for higher level stuff, you can easily use it as a self-contained device. Okay, so the basic idea was naturally for reverse engineering. So this means if you, for example, examine the protocol of MIFARE, that at one point you have the opinion, okay, it could work like this, and then you can use this device to instantly test your assumptions. So this is a tool for iteratively reverse engineer protocols, and you find out what's important in a protocol and what not. So the device, because we have this, we can actually demodulate the reader data that we see. You can also use it as a dump sniffer. You can just, the range is not very good, but you just put it between the reader, and your real card, and you can easily get the decoded digital data over DMA. So you can reverse engineer simple cards very quickly, and you can even do a replay attack easily, because you have the same possibility. You have the possibility to send out data which is directly sent to the load resistors, which form the reverse path to the reader, and you can directly take the sample data and replay it. So possibilities like taking the device, using the internal button to record a card which is in a briefcase somewhere or in a bag, whatever, and then use it again to replay it in the door step. So these attacks are already possible with this device. One main cause is also fuzzing attacks. So because we are in full control of even the lowest layers of the protocol, we can introduce all kinds of violations. So you can see me automatically violate different areas and look how the readers react to it. If it breaks, if it stops, and it's a perfect tool for this, in my opinion. Because you can sniff data with this, you can obviously, as long as you know the algorithm which is behind it, you can use it for offline key cracking. And if you do the full emulation, you can replace your lost RFID tags, you can create backups. Okay, what's still missing? So you're getting a rough idea where we are currently at. We are currently working at the anti-collision, which is exactly this nasty part where you have to use very tight code, where we have to comply to very tight timing constraints. And the great thing about this is, as soon as the anti-collision is over, we are set. Basically, you only have to do this is the only place where real time is vital. All other places could be emulated on the PC. So this means that if you have this device, you are able, as soon as you have the anti-collision over, to take over from host side. So you can develop a complex application locally on your host PC. You can locally debug it, and it will supply the necessary data over RF interface and the therefore virtually emulated tag. And because we are full control, we can behave like 2, 3, or 1,000 devices virtually, because we can basically send collisions easily. This, for example, enables to exploit this anti-collision algorithms, and, for example, allows easy denial of service attacks on readers. So you can basically stop it. You don't need a bag with 10,000 of cards, which won't work anyway, but you just use this device and behave like you were an insane amount of tags. And you can do this in a clever way. You can, for example, leave random spaces and whatever. So I think it would be very, very hard, I think in my opinion impossible, to fight against such attacks, because you are in full control, because it's software in the end. And what we want to see in future, I think this is a very hard task, is this version of MyFair encryption algorithm to again prove the world that proprietary algorithms that nobody knows how they work are not a good way forward. So I think this could prove an important tool for doing such tasks. And what's currently low priority is ISO 15693 emulation support. It's basically only the bit layer, and the timing constraints are less critical, basically. Okay, so what we want to achieve in future. Currently we have hex dump, so this is not very readable. It works really reliable. If you send thousands of packets, you get basically only a few packets that have errors in it. So it works stable in this aspect. But what we obviously need is some tool that knows the protocol, decodes the bit patterns, knows about protocol state, and provides a nice verbose output like we are all used from TCP dump and other tools. Yeah, and as soon as the basic ISO 14443 and ISO 15693 support is up, it's very simple to add emulated card profiles. Because we have plenty of space there, you can even emulate multiple different cards with the same device. So as soon as they're documented, it's only a matter of hours or days to implement such a protocol based if you have the bit layer set. So say anti-collision and the modulation demodulation. So what we expect is that as soon as we provide this tool, that other people will come and implement all this proprietary RFID protocols, so others can again play with this and check the underlying software layers for problems. So this is the basic intention. And what would be also nice is just to do this copy and paste action with electronic passports. Harold?